Hello, everybody. This is the video to help you prepare your report for thermodynamics. And here I have the report sheets. I just want to let you know that the best thing you could do to prepare this report is to really read and study the background in this electronic file, because everything that you need is in there, including the experimental setup. But anyway, let's get right to the questions for your report. Number one, what do we expect for the magnitude of KSP for this particular insoluble salt? Now remember, in this study, what was supposed to be done is solid samples of potassium nitrate were dissolved in solution. So this equilibrium here is set up, and you were supposed to tell whether the equilibrium constant for this reaction, KSP, which you should be able to define as the concentrations of the products to their stoichiometric coefficients, which is 1 over the reactant, but the reactant's solid, so it's not in there in the expression for KSP. Whether you expect that to be greater or less than 1, that depends on whether you think this reaction should lie to the right once at equilibrium or to the left. And now how would you know that? Well, you should know that from Chem 200 and your knowledge of how these type of salts behave in water. So if you don't look it up, look up what kind of bonds going on in there and what the solubility rules are for potassium nitrate. Number 2, do you expect the dissolving of KNO3 to be endo or exothermic? Why? So you want to look at, again, the interactions of what's in the solid and what needs to be broken up. And I think after you research it for a while, you'll see it's an ionic bond because it's a metal non-metal. You know that from Chem 200. The non-metal portion is the nitrate, NO3 minus. So there's an electrostatic interaction, and you're going to have to supply some energy to separate those ions of different charge. So I think that's enough hint for you to figure out what's going on with the thermonicity of that reaction. Number 3, do you expect the entropy to increase or decrease? Here you should look back at your definition of entropy and see that it's a measure of the dispersion of particles and or energy, and therefore you can come to a conclusion as to whether that increases or decreases during that process of dissolution of potassium nitrate to potassium ions and nitrate ions. And use that knowledge to explain why you believe it. 4, based upon what you know of nitrate salts, should that dissolve spontaneously? Explain. So here you're going to talk about your Chem 200 solubility rules. Excuse me. Using the literature values in the presented table, that's these guys down below, you are to calculate the delta H, delta S, and delta G for this reaction. And they do an example of delta H for you, so you have to find the appropriate equation for delta G and delta S, which looks similar to this one here, and use the values in this table to calculate well, delta G and delta S, because they've done delta H for you. And you can see from the formula, it says take the sum of the delta H of formations of the reactants, which you want to subtract that delta H from the delta H of the products. So in the equation, it shows you, okay, the delta H of the products are these two here. They're the products. And so I have this delta H represented here, and this delta H represented here. And then lastly, this guy over here to get a estimate of the delta H of reaction. So it should be endothermic according to these theoretical values. And you're going to put those values in the table here, here, and here. Okay, moving right along, use the mass of potassium nitrate to calculate the number of moles, and that's in table 1, the Excel spreadsheet file that was also supplied to you. The mass in that Excel spreadsheet is around 20 grams, right? It's 20 point something, something, something. So you can figure that out. You divide that by the molar mass, and that gives you the moles. Boom, done. Number 7, determine the total amount of water delivered. So that's from the burette readings, and you should know how that was done from reading the background on what was supposed to be conducted during the experiment. And essentially for this number 7, all you need to do is take the final burette reading and subtract the initial, and that gives you the amount of water delivered. So you can calculate that, put it in the table. Then you're going to take the average of the saturation temperatures and put that also in the table. You should know what that means, the saturation temperature. And again, that's in the background. That's the temperature at which there's an equilibrium between the tiniest speck of solid and the ions, potassium and nitrate in solution. So there's these different equilibriums with different concentrations that are established at different temperatures. And it says here, I see it says from the 3 T values given. So you just need, they did the experiment 3 times, the same one, then you just average them, and then they moved on to the next experiment, did it 3 times, and so forth until they went through 5 experiments. So you need to average the 3 temperature values for each of the 5 experiments that were run during this data set. Okay, 9, fill the average temperatures. So once you have those averaged, just copy them into table 2 and 3. And then you're going to go on to table 3 and figure out the molar concentration of potassium nitrate. So that's moles per liter. You have the total solution. So to calculate the molar concentration, remember the definition of that is molarity, and that's defined as the moles of solute over the liters of solution. So the moles of the solute you calculated previously. The liters of solution, that's going to be found in the graduated cylinder reading. This isn't the final minus initial burette reading, that because the final minus initial burette reading, that's just the milliliters of water that's delivered. What we want for molarity is the volume of the whole solution. So that's, of course, that milliliters of water that's delivered, but also it includes the volume of that solute that's dissolved in there. So it's going to be a little bit more, and that's how you calculate molarity. So remember that definition. All right, so we're through 10, we go to 11, use equation 5, which comes from the ice table to calculate the KSP, the solubility product constant. So if you look at, again, in the background for the definition of this KSP, you'll see that it has that equilibrium that we wrote up here, right here, all right? But then you'll see underneath it, there's a ICE, the solids like this, initial, and the S's look like that. So now you can see that the KSP is defined as S squared. So you just need to take these concentrations, which are the same, and square them. All right. And so you should be able to calculate the KSP at each of the 5 different saturation temperatures. Put those in that table. Number 12. Now, for number 12, they want you to calculate solubility in a different way with different units. So before we calculated solubility in units of molarity, right? But now they want you to calculate the solubility in units of grams of potassium nitrate per 100 grams of H2O. Okay, so that's another way to define a different solubility. So you're going to do that for each case. And for example, the first case, you would take very simply for that run 1, it would be that around 20 grams that was dissolved in approximately 15 milliliters. I think in the Excel spreadsheet, let's just pop that up and look, we have, yeah, so the amount delivered for that run 1 case is final, which is 15.05 minus initial 0.00, so it's just 15.05 milliliters was the total amount delivered of water. So we would have that 15 right here in that position, because that was, it was actually 15.05 grams, right? Because 15.05 milliliters, if you use a density for water of 1 gram per milliliter, sorry, 1 gram up here on the top per 1 milliliter on the bottom, then the milliliters cancel out and you get grams. So this is also equal to grams here. And that would be the solubility for the first run. The second one, you'd add approximately 5 more grams to this because 5 more milliliters were introduced, so it would be around 20. The next one will be 25. The next one after that would be 30, and the one after that would be 35 grams. But you're going to do it exactly looking at the amount of water that was delivered from those burette readings. Know that those volumes can be converted to grams and then calculate the solubility for each case. Okay, now it says use the Excel graphing function or whatever software you want to use to plot this. You can even do it by hand and upload it. But you're going to make a plot of the solubility in those units. So this one is the solubility in these units versus temperature. So you're going to have 5 points. It's probably going to look something like that, and you can plotted or whatever. You don't have to fit it to a line it doesn't say to. Now, once you get that, you're going to compare that to your textbook solubility versus temperature for potassium nitrate. You can also look this up online, and you're going to see that it's going to look something like this versus temperature. And you'll probably have a whole bunch of other compounds in there, and it might look like that. And one of those is going to be identified with the potassium nitrate curve, and you'll see how it looks different than yours. But what you have to realize is that your temperature range is much smaller than the published one. So your temperature range may only be from here to here, so it looks linear in that range, and that's why your plot looks linear, but it does curve when given more temperature values. So they want you to do a comparison, and so you can say, well, it's similar. But even a better way to do it is to maybe calculate a percent difference at some temperature that you choose. So you take one of your temperature values, right? You find its solubility, and then you go over to the literature value and make sure that you get the right temperature. You go over to their solubility, and then you can take a percent difference between the one that you got and the one that is in your reference plot. All right, 15, in table 4, convert the average temperatures to Celsius, Kelvin, and 1 over Kelvin. You can do that. Then they want you to calculate the corresponding delta G's given those KSPs that you calculated using the ice table and just taking the solubility squared. So you can plug it into that formula and generate 5 delta G's for those 5 different saturation temperatures. 17. Now use Excel to make a plot of the ln of those KSPs versus 1 over temperature. Now, why would you want to do that? It seems kind of funny. Well, if you remember from the background, there's a special equation that's derived from 2 that you should know, and that's the one with delta G that equals delta H minus T delta S, but also delta G equals minus RT ln K. So when you equate these two and then you isolate just for the log of K on one side, then this is the equation that you generate. And now this shows the functional form of how the equilibrium constant KSP varies with temperature. So this log of KSP is like the dependent variable, or y, and the 1 over t is the independent variable, or the x. So when you make this plot, you're going to get something like this, ln k sp versus 1 over temperature. And you're going to get your 5 values, and hopefully they look something like that, and you can plot it and have Excel fit that to a straight line, and therefore you define, or Excel gives you, the m value, the slope, and the intercept value. Now, looking back here at the equation of a line and how it relates to this relationship of K and temperature, you can see that the slope is going to equal delta 8 minus delta H over R, and the intercept is going to equal B. So if you know B and you know R, 8.314 joules per mole K, then you can calculate delta S. N, if you know M, which you will once you do the plot and have Excel tell you the slope of that line, then you'll be able to use M as a value and calculate delta H. And you see that the slope is negative, so M is negative, so the negatives cancel out and gives you a positive delta H, which, as you recall from our calculation using the theoretical values, delta H came out positive and it was endothermic. So you should have a negative slope on this plot. If not, then you're probably doing something incorrect. Okay. So you're going to put those values of experimental delta H and S in the table 5. Then you're going to, in 19, you're going to use the experimental values to calculate the delta G value at 25 degrees and put that into table 5. So you want to calculate delta G based off of those experimental values, the delta H and delta S you just determined from the slope and the intercept of that line. And then, of course, you're going to put in 25 degrees Celsius here or 298 degrees Kelvin. Number 20, compare percent error in your experimentally determined values for delta G, H, and S at 25 degrees to the theoretical values, table 5. So for 20, you could maybe make up another table and just take a percent difference between all those three quantities. One that you obtained experimentally with the plot, and number 20, and the other theoretically that you calculated using those summation equations for the delta H, G, and S that were given in the table. So you should be able to accomplish 20. For 21, discuss the signs of the experimentally determined delta G, H, and S at 25 degrees in terms of spontaneity of the dissolution of potassium nitrate in water. Does it match your predictions in questions 2, 3, and 4 that we looked at above? Remember, you had to predict whether the reaction was going to take heat to break up the ions, for example. And since we said, oh, it's an ionic interaction of positive and negative, of course, it's going to take energy to pull them apart. So it should be endothermic. That's all in your explanation of question 2 above. And so, yeah, that would make sense for H. H should be positive, delta H of reaction, because it takes heat to pull the potassium from the nitrate away from each other in the crystal and dissolve it and make it aqueous in the water solution. And so you're going to do the same thing with delta G. What's the sign of delta G? And does that make sense? In other words, is the dissolution of potassium nitrate spontaneous in water? If it is, delta G better be negative. Delta S, does it spread out particles more so, or does it spread out energy more so? Because if it does, then delta S should be positive. And so you're going to think in terms of what's happening in the reaction, use the definitions of H, G, and S to explain why that makes sense, and show me that you understand those definitions in this specific application to the dissolution of potassium nitrate into its ions. All right, good. Now, 22, compare the 5 calculated delta G's in table 4 to the delta G at 25 that you just calculated back here in 19. and see if it makes sense. Do they fall? Does that one that you calculated, does it fall in line? So you have to look at those delta G's and note that all the delta G's, the 5 that were presented in this experimental data, are all higher temperature. So this delta G at 25 degrees should fall in the beginning or the end of that series, into that trend. And if it does, then you should kind of make sense of why it does from your knowledge of what delta G is. Now, remember, delta G is the change in the Gibbs free energy from the products to the reactant. And the larger that magnitude is, the further away equilibrium is from your starting situation. And you can use things like that to explain why that value is what it is and why it falls in line with the others. And you're going to just follow those directions, answer those 22 questions or statements, and upload everything that it asks you to back here in the beginning for your report. So make sure you have all of this stuff. And that's it. So hopefully that'll get you started in making this report. If you have any questions, please feel free to post them and I'll get to them as soon as possible. Thanks for your attention.